So, Jai Hind everyone. My name is Ritesh Sharma. I am from AKGEC Garg Engineering College, Ghaziabad, and I am taking subject of Fundamental of Electrical Engineering in first year. The subject code is BEE 101 and 201 in odd and even semester. So, today I am going to take the topic of unit number 4, the DC machine. So in DC machine, so I'm going to discuss the topic of the basic principle of working principle of DC generator and EMF equation and the types of generator. So let's start with the first. So these are the topics which I just told you: the working principle of the DC generator, then EMF equation, and then we will discuss about the, if the time permits, we will discuss about the types of DC generator. So if we are talking about the working principle of DC generator, so it is well known that according to the Faraday law of electromagnetic induction, when the conductor moves in the magnetic field, by simply you can say the cutting the magnet, when the conductor moves in the magnetic field or rotate in a field, it will cut the flux, and a dynamic induced EMF is produced in the conductor. So whenever there is a relative motion, some voltage will be induced in the conductor, and the magnitude of the generated EMF can be given by the EMF equation of the DC generator. So whenever the voltage is induced in the conductor and if the path is closed, the current will flow in the conductors and the current will flow in the circuit. And since the circuit basically it consists, which is connected to the load of the circuit. So in DC generator, when the armature is rotated with the help, because we are rotating the armature with the help of prime movers, because in generator we know that the mechanical energy is converted into the electrical energy, and this mechanical energy is provided by the prime movers, and the field windings are also there, and the field windings are excited, which will produce a flux in the circuit. So EMF is induced in the armature conductor, and this induced EMF is taken out via commutator and brush arrangement, because we all know that the EMF is which induced in the winding of the armature is AC, and then AC voltage is converted into DC with the help of your commutator, and it is taken out, the unidirectional current is taken out with the help of brush arrangement. So let us discuss in more detail about the generation of the voltage in the in generator. The direction of the current. The very important part is that how do we find the direction of current in a DC generator. So for this we have the Fleming right hand rule. The Fleming right hand rule says that when we stretch our finger, the thumb, index finger, and your middle finger, the thumb indicate the direction of motion or the force, the index finger indicate the direction of field, and your middle finger indicate the direction of current. So when we apply this the Fleming right hand rule, we will find the direction of current in a circuit. Suppose in a figure shown, the direction of current is suppose in the conductor is going this direction. So suppose that and the motion in this direction. So if the current is this direction, field is from north to south, ultimately the force will act on this coil to rotate in this direction, that is in clockwise direction. Or we can say that if the coil is rotated in clockwise direction, means force is acting on this coil is upward, means this, and the flux is going from north to south, so that we can say that the direction of current will be in this direction. So this is a simple, you can say, a method to determine or the direction of current in your DC generator. So to find the or how the voltage is induced in a particular generator, let us consider a single coil. Let us consider a single coil, and this coil is rotating in a clockwise direction. Okay, if the rotation is clockwise rotation. So field is from north to south. So north to south is the field. So suppose that at position 1, when this coil is at one position, we can say that the field and your coil is in parallel to each other. So there will be no flux induced in the armature winding in a coil. So at one position there will be a zero voltage induced. Okay, now when we change to the position number 2, so there might be some angle, and because of this inclination angle there will be some voltage induced in the coil. So at position 2 there will be some position, suppose the angle is 45 degree here. So at 45 degree there will be some voltage induced in the coil, and when it reaches to position number 3, at position number 3, that is the voltage or the flux cut by the coil will be maximum, and there will be the maximum induced voltage in the coil. So similarly, at different position, the voltage will be induced in the coil, and when we trace the graph, it will be a sinusoidal. So it means that the voltage induced in the coil of armature, simple, this is a sinusoidal. So this change in the flux linkage induce the EMF in the coil, and the induced EMF in the one coil side and the induced EMF in the other. So that it means that when the coil is at under the north pole, suppose the current is in this direction, and when this coil is under the south pole, the direction of current will be different. So that hence the current direction will be changes like this, or sorry, voltage. So this is a simple example to understand the voltage induced in the armature of the DC generator. Now the following points, the EMF induced in the generator can be explained as follows, which I told you just now. When the loop at position 1, the generated EMF is 0 because the movement of the coil side is parallel to the magnetic flux. Okay, the first point. So here at position 1, it is the coil side, the flux is in parallel with the coil side, so it is 0. When the loop at position 2, the coil sides are moving at the angle to the magnetic flux, and hence a small EMF is generated. So as I told you, at position 2, there will be some voltage induced in the coil. And when the loop at the position 3, the coil sides are moving at right angle to the magnetic flux. So when the coil side at right angle, it will induce the maximum voltage in the coil. So the maximum voltage at point 3 and so on. So if we draw a graph, it will be a sinusoidal. So it is clear that the generated EMF in the loop is alternating. So when we draw this, it is clear that it is a alternating one, and it is because any coil side has EMF in one direction. EMF in one direction. EMF in one direction when under the influence of north pole, and in the other direction when under the influence of south pole. So different direction of the current when EMF in one direction and under the influence of north pole, and in other direction when under the influence of south pole. So two different polarities this is. When the load is connected across the terminal of the generator, an alternating current will flow. When the voltage induces will be there, when we connect the load, it will be alternating. Okay, so but our requirement is a DC. So when we using with the help of commutator, this alternating EMF generated in the loop can be converted into the direct voltage, that is a DC voltage, with the help of commutator. So the function of commutator is to convert the AC voltage into the DC. So now let us derive the EMF equation of the DC generator. So EMF equation of the DC generator. So what are the basic requirement for the EMF? First of all, there is a magnetic flux per pole phi. The flux generated produced by per pole. Suppose if we have a 4-pole machine, so this phi is the flux produced by one pole. Z is the total number of armature conductor. P is the number of pole in a machine. A is the number of parallel path in a circuit. The number of parallel path will depend upon the windings. Okay, how the armature winding is connected, whether it is the lap winding or wave winding. For lap winding, the parallel path A will be equal to number of poles, and for the wave winding, the number of parallel path will be equal to the 2. N is the speed. Suppose that is the armature is rotating with the speed of n rpm, and suppose that generated EMF is this. So to derive this, let us suppose that we have assumed that phi is the flux per pole in a Weber. So the total flux in whole when the your coil is rotated by one revolution, for one revolution, the total flux will be the total flux cut by coil is equal to P into phi, because phi is the flux per pole. If the P is the number of poles, so that will be equal to P phi. Okay. Second one is that the time taken, how much time will be taken by one revolution. So suppose that if the n revolution is taken by in 60 seconds, because n is the RPM, revolution per minute. So n revolution is taken in 60 seconds. So one revolution by 60 by n second. So in one revolution, time is taken in 60 by n. Hence, the induced EMF will be equal to, given by the change of the flux by the time taken in one revolution. So one revolution, how much d phi will be equal to? Your P phi, it is the total change, and in dt, it is given as 60 by n. So this will become P phi n upon 60. This is the voltage generated by single coil. And we know that the total number of conductors are Z. If the Z is the total number of conductor, so total the voltage induced, average voltage induced in a conductor will be given by this P phi n upon 60 into total number of conductor per parallel path. Where Z is the total conductor and A is the total number of parallel path. So, and this value of A obviously depend on how we are connecting the armature winding, whether it is lap winding or wave winding. So this equation can be written like this equation can be written phi Z n upon 60 into P upon A. This is the voltage generated in a armature coil in volt, where A is equal to P for lap winding, and A is equal to 2 for wave winding. We already gone through the concept of lap winding and wave winding in the lecture of construction of the DC machine. Okay, so this is the generated voltage in a armature coil, or average value of generated voltage in the coil. So this is in the volt. Phi is the flux per pole, Z is the total number of conductors, N is the speed, P is the pole, and A is the parallel path. So this is how we can determine this is the voltage. We know that the voltage induced in a conductor, that is d phi by dt. The total change in the flux upon total change or total time in one revolution. So when the coil is rotated by one revolution. So this is the EMF equation of the DC generator. Now after that, the EMF equation, the types of DC generator. So the types of DC generator. So DC generator are basically classified based on the way in which the field winding is excited or connected. How we are exciting the field winding. So generally it is the DC generator are separately excited, or it may be self-excited. How the field windings are excited. So based on that, separately excited and self-excited. When the field winding is excited separately, separate DC source, it is called separately excited. And when the field windings is excited with the same generator, with the same flux or same current, it is the self-excited. And further, the self-excited DC generator are classified as shunt generator, series generator, and compound generator, depending upon how the field winding is connected. Okay, so let us understand first the separately excited DC generator. So if you can see the picture or the circuit of this separately excited, so in this circuit we have the armature, which is rotating armature is there. So voltage armature having some resistance also, armature winding have some resistance. So resistance is RA. So armature RA is a armature winding resistance. Then field current. The field current, since it is a separately excited DC generator, so the field current which is provided, the field winding is excited separately by the DC supply, some separate DC supply. So that's why we call it the separately excited DC generator. So IF is the field current which is given to the field winding. So why we are giving field winding current? Because we need to excite the poles, and therefore the flux, then the field flux will be there. Okay, and that flux will be cut by our rotating armature. IA is the armature current. IA is the armature current when this armature is connected with the load. So obviously the current will flow. That is called IA. IL is the load current, and V is the terminal voltage. The V is the terminal voltage of the load of armature side. So if you write the voltage equation of this, so it's very simple. So suppose that the voltage generated is EG. EG is a voltage generated. So simply we can apply the Kirchhoff voltage law, and this EG will be equal to this V. EG will be equal to voltage V plus the drop in this winding resistance. So EG will be equal to if we apply the KVL, so EG minus IARA minus V, and minus VBR is called the brush voltage drop. So these are the brushes basically, and this brush voltage drop, if it is given, we have to consider it. Okay, so this voltage drop, suppose it's a VBR, it's a brush drop, brush voltage drop. So from this we can say that the generated voltage is equal to IARA plus V and plus VBR. So we can calculate the terminal voltage or the required parameter from this equation. This equation is called the voltage equation of separately excited DC generator. So the two terms are here, the power developed in the DC generator. How much power is developed actually? The power developed in generator, if you see that armature, the voltage is EG and the current is IA. IA is flowing like this. So EG into IA is the voltage, power developed in the generator. So how much power is developed? So it's the multiplication of generated voltage and the current flowing through the armature, which is IA. And the power delivered to the load, how much power is delivered to the load? That is called the load having some voltage V. V is the voltage and IL is the current, that is called the load current. So since here IL is equal to IA, okay, so this is equal to V into IA or IL. So this is the power delivered to the load. So in separately excited DC generator, it is very important that the field windings is excited from the separate DC supply. Okay. Now take the example of separately. In case of separately excited DC generator, very important part is that the self-excited generator produces the DC output, okay, whose field windings are excited by current produced by generator itself. So it's field winding which is being excited by generator itself. No separate source is used for field. That's why we call it the self-excited DC generator. Now, so in this particular type, it is very important that some flux is already present in the pose due to residual magnetism. So the basic requirement of these types is your pose having some residual magnetism. Because of that, it has some flux in your pose, and this pose will create some voltage induced in your armature, and this will accumulate. Okay, when it will have some voltage induced, then because of that it will give some current to the field winding. Again, the field winding is excited, having some more field current, and this process will be continued. We call it the voltage build up in a DC generator as far as the self-excited DC generator is concerned. So if we talk about the classification of the self-excited DC generator, so we have three types of self-excited generator. First is called shunt wound, then series wound, and then compound wound, as we discussed earlier. This is our shunt wound generator, the series wound generator, and compound wound. It is basically depend upon how your field winding is connected. If your field winding is connected in the parallel to the armature, it is called shunt wound generator. When the field winding in the series, we call it the series wound, and when the field winding is both in series and shunt, and we call it the compound wound DC generator. So we will discuss one by one, or at least we will discuss the circuit of this, so that we can understand the concept of how this the voltage is generated actually. The voltage equation is this. So if you can say that this is the simple example of DC shunt generator. In DC shunt generator, we can see that the shunt field winding is connected in parallel with the armature. So when there will be some flux in the field winding, in the field pose, there will be some voltage induced actually, and that flux will induce some voltage, and because of this some voltage EG is there, because we know EG is equal to phi Zn upon 60 into P upon A, and this generated voltage is proportional to flux and speed, because Z is constant, P is constant, A is constant. So this voltage induced is proportional to flux and your speed of the armature. So based on this, the flux, the generated voltage can be increased, and because of this voltage induced, the circuit is closed, the current will go like this and it will split like this. So when it will go to the shunt field winding, and this is the load winding, load connected in the circuit. So in DC, in this types of the field winding is connected across or in parallel with the armature, and the field winding has a more number of turns, and a thin wire having the high resistance is this. So this is the basic construction of this. And the load is connected across the armature as shown in the armature, and a small amount of current will flow through the field winding, and the more current will flow through the armature. So small current, because in the resistance of this winding will be more. This suppose if it is RSH, the resistance is more, so small current will flow through this. Okay, and the current through the load will be more. So if we write the equation, the voltage equation of this, so voltage is given by, since IA is equal to IL plus ISH. So IA is equal to ISH plus IL. The current is going from the armature as going to the field and the load. So IA is equal to this. And the shunt field current ISH will be given by this. ISH current will be equal to how much? Is equal to the voltage is V upon RSH, where RSH is the shunt field resistance. So terminal voltage will be given by this expression. V is equal to, because this V will be equal to EG, voltage induced in the armature, minus the resistance and the brush drop. The brush drop will be in this, because these brushes are of carbon or graphite, so it will some drop will takes place around 1 volt or 2 volt. So this is the equation. And similarly, we can calculate the volt power developed in the generator. So in the current in the generator or armature, the voltage induced is EG and the current is IA. So this is the power developed, and the power delivered to the load. So we are delivering load. So load is voltage is V and the current is IL. So it will be V into IL. So this is the voltage equation as far as the DC shunt generator is concerned. Okay, so now let us take the example of a series generator. In DC series generator, we say that this is the field winding, and this field winding having a less number of turns, because as compared to the shunt generator, because this winding is in series, so this resistance must be low, so having less number of turns. And one more thing is that the current flowing in the armature is flowing through the series winding, and same current flows through the load, since there's a series is this. So only one current flowing in this particular circuit. So the load is in series field winding, and armature conductors, all are current are flowing through the field windings and the load. The same one current, that armature current is flowing through the series as well as load. So the voltage equation will be series current, armature current, IA the load current, armature resistance, armature terminal voltage, brush contact drop. So you can say that the voltage equation will be given by this. So V will be equal to generated voltage and the drop in the armature, again the drop in the series field winding and brush drop. So this will be the equation, voltage equation of the DC series generator. Again, the power developed in the generator. If you see the circuit diagram, the power developed is given by the voltage. It is the multiplication of voltage and current. So generated current voltage into the current, that is the armature current. So this is the power developed, and the power delivered to the load is the V into IL. So V is the voltage in the load, across the load, and current through the IL, and IL is equal to IA here. IL is equal to IL. So this is the voltage equation of series generator. So in today's lecture, we have seen the some important topics of the basic principle of generator, how the voltage is induces and the nature of the voltage. It's a sinusoidal in the armature. Then we convert into the DC with the help of commutator. That is the action of commutator is this. We will discuss in the next lecture the action of commutator or the working of commutator. Then the voltage or the EMF equation. EMF equation. So in EMF equation, this is the EMF equation of the generator, phi Zn upon 60 into P upon A. So A is the number of parallel path and A differ as for the lap winding A is equal to P and for the wave winding A is equal to 2. So this is essentially for the simplex, it's a simplex winding. Simplex winding because this lap winding may be simplex, duplex and triplex. So based on that, it is A is equal to P or A is equal to twice of P or A is equal to thrice of P is this. But for the basic fundamental, we generally use the simplex lap winding actually. And then we have the classifications. So separately excited and self-excited DC generator. So in this lecture, in the next lecture, we will discuss about some compound DC compound generator like long shunt and short shunt. So thank you so much.